The cosmos is a masterpiece of repeating patterns. Is that beauty just a cosmic accident, or is it a clue to something deeper, beneath the chaos of exploding stars and swirling galaxies? Physicists believe there is a hidden language of perfect order, a secret code written in symmetry. Symmetry is not just about pretty shapes. It is the fundamental principle that dictates how particles interact, forces emerge, and reality itself holds together. By the end of this journey, you will see the universe not as a random collection of stuff, but as an intricately woven tapestry governed by elegant, invisible rules. We are going to explore 30 mind-bending theories, from the rock-solid to the wildly speculative, that attempt to decode this cosmic cipher. What if the force of gravity and the tiniest quantum particle are two faces of the same symmetrical coin? What if our entire three-dimensional world is just a holographic projection from a two-dimensional boundary? The search for this hidden symmetry is the greatest detective story in science. What single idea about the universe feels most beautifully inevitable to you? Our journey into the hidden order of the universe begins not with wild speculation, but with the most successful scientific theory ever created. It is the bedrock of modern physics, a framework so precise it can predict the outcome of particle collisions to a staggering number of decimal places. This is the Standard Model, and its entire architecture, every single equation, is built upon one beautiful mathematical idea: gauge symmetry. Think of the universe as a grand stage. The fundamental particles, like electrons and quarks, are the actors, but they are not free to do whatever they want. They must follow a script, a set of rules that dictates how they move, interact, and transform. Gauge symmetry is that script. It is a kind of cosmic rule that says the laws of physics must look the same, must remain perfectly symmetrical, even when we change our perspective on the particles in certain mathematical ways. This might sound abstract, but the consequences are utterly concrete. Every fundamental force we know, except for gravity, emerges directly from enforcing a specific gauge symmetry. Electromagnetism, which gives us light and holds atoms together, comes from a relatively simple symmetry. The strong nuclear force, which glues protons and neutrons inside atomic nuclei, comes from a more complex one. In this view, forces are not things that push and pull from the outside. They are the inevitable side effects of the universe demanding perfect symmetry. The particles themselves are like actors who must wear different costumes depending on the scene or the symmetry they are obeying. A single actor, an electron, can play different roles in the electromagnetic scene. But to participate in the weak nuclear force scene, it needs a different partner, a neutrino. The mathematical groups that describe these costumes have names like SU3 and U1, which sound intimidating but simply represent the different ways particles can be rotated or shifted in an abstract space while keeping the cosmic play consistent. There is, however, one glorious complication in this perfectly symmetrical script. If the symmetry were perfect everywhere, all particles would zip around at the speed of light, weightless and ethereal. There would be no atoms, no planets, no us. Something had to break the symmetry just a little to give substance to the world. That something is the Higgs field. Imagine a crowded room where a famous person enters. Everyone clusters around them, and their movement through the room slows down. In the universe, the Higgs field is like that crowd. Particles that interact with it strongly, like the top quark, wade through it slowly, gaining what we perceive as mass. Particles that barely interact, like photons, zip through untouched, remaining massless. This Higgs mechanism is a gentle, specific breaking of the gauge symmetry. It is not a destruction of the underlying order, but a subtle bending of it, allowing the universe to have both elegant rules and tangible stuff. So the Standard Model presents us with a universe of breathtaking hidden symmetry, where forces are mathematical necessities and mass is an acquired trait. But this magnificent theory, for all its power, is incomplete. It leaves one colossal force entirely off the stage. Gravity refuses to follow the script. Gravity is the stubborn rebel, the one force that refuses to join the elegant symmetrical dance of the standard model. This glaring omission is the crack in the foundation, the clue that tells physicists their map of reality is still incomplete. To mend this crack, they have proposed one of the most beautiful and ambitious extensions of symmetry ever conceived. It is called supersymmetry. This theory whispers a stunning possibility. What if the fundamental division of the universe into matter and force is itself an illusion? Supersymmetry proposes a hidden, deeper layer of order where these two great families of particles are not separate at all. They are mirrored reflections, two sides of the same coin. In this symmetrical world, every fermion, every particle of matter like an electron or a quark, would have a bosonic superpartner. And every boson, every force carrier like a photon or a gluon would have a fermionic twin. The electron's superpartner is the selectron, the photon's is the photino. It is as if the cosmic play suddenly doubled its cast, with every actor getting a shadow partner who plays the opposite role. The motivation for this elegant doubling is profound. It solves a nagging mystery known as the hierarchy problem. In the standard model, the mass of the Higgs boson is incredibly fragile. Quantum fluctuations from known particles should drive its value to an astronomically high number, making our universe impossible. But supersymmetry introduces the superpartners. Their quantum contributions perfectly cancel out those of their ordinary partners, like two waves crashing together and flattening into calm water. This natural cancellation protects the Higgs mass, keeping it light and stable, and in doing so, it stabilizes reality itself. Furthermore, this new symmetry brings the forces of nature closer together. In the high-energy chaos of the early universe, the strengths of the electromagnetic, weak, and strong forces may have been identical, united by supersymmetry into one grand, symmetrical force. Most tantalizingly, the lightest of these superpartners would be stable, invisible, and permeating the cosmos. It would not interact with light, yet it would have mass and gravity. In other words, it is a perfect candidate for the mysterious dark matter that binds galaxies together. For decades, supersymmetry was the frontrunner, the theory so beautiful it simply had to be true. Yet, when the Large Hadron Collider began its search, it found the Higgs boson but no sign of the selectron, the photino, or any of their siblings. The symmetrical partners, if they exist, are hiding at energies far higher than we have probed. So supersymmetry remains in a strange limbo, a breathtaking idea that has not yet shown its face in our experiments. Its elegance continues to inspire physicists, a ghostly symmetry waiting in the wings, reminding us that the universe's deepest secrets may still be written in a language we are only beginning to decipher. The absence of supersymmetry at our current energy scale does not mean the symmetry is broken. It simply means the stage we are observing is too small. To find a place for gravity in the symmetrical fold, we may need to radically reimagine what the actors themselves are made of. This leads us to perhaps the most ambitious framework in all of physics, string theory. In this view, the fundamental ingredients of the cosmos are not zero-dimensional points, but unimaginably tiny, one-dimensional loops or strands vibrating. A single string, thinner than a proton by many orders of magnitude, can vibrate in different modes, just like a guitar string can produce different notes. And here is the breathtaking part: the note it plays determines what kind of particle it becomes. One specific vibration might correspond to an electron, another to a photon, another to a graviton, the hypothetical particle of gravity. In this single, elegant idea, all matter and all forces, including gravity, emerge from the same basic entity. The symphony of the universe is played on these cosmic strings. The profound beauty of string theory is its absolute reliance on symmetry, but of a kind that demands a shocking expansion of reality. For the mathematics of these vibrating strings to work consistently, to avoid nonsensical predictions, they require more space to move in. They need extra dimensions. We are not talking about 1 or 2. The most popular versions of the theory require a total of 10 or even 26 dimensions. We experience only 3 of space and 1 of time. The rest are hidden from us, curled up into shapes so incredibly small that even our most powerful instruments cannot detect them. The nature of these hidden dimensions is not random. They are folded into exquisitely complex, symmetrical shapes known as Calabi-Yau manifolds. Picture a garden hose from a great distance. It looks like a simple one-dimensional line, but up close you see it has a circular, two-dimensional surface wrapped around its length. Now imagine that circular cross-section is not a simple loop, but a fantastically intricate, multi-dimensional shape with holes and twists, a shape of perfect mathematical harmony. That is a Calabi-Yau manifold. The specific geometry of this hidden shape, the number of holes it has, its precise contours, dictates how the strings within it can vibrate. In this way, the symmetry of the Calabi-Yau manifold directly determines the symphony of particles we see in our three-dimensional world. The mass of an electron, the charge of a quark, the very number of particle generations, all could be locked into the topology of these unseen dimensions. String theory presents a universe of staggering hidden symmetry, where the diversity of reality is a direct consequence of the elegant, compact geometry of space itself. We are, in a very real sense, living in the shadow of a magnificent, higher-dimensional sculpture. Yet, for all its mathematical beauty, this theory remains just that, a theory. It makes predictions at energies far beyond our reach, and there are countless possible Calabi-Yau shapes, perhaps as many as 10 to the 500, leading to a landscape of possible universes. This immense flexibility is both its power and its greatest challenge. If every possible shape exists somewhere, what determines the specific symmetry that gave birth to our cosmos? But if string theory's hidden dimensions feel abstract, the next idea is utterly revolutionary. It suggests that our entire three-dimensional reality, with all its stars, planets, and people, might be nothing more than a projection. A cosmic illusion. This is the holographic principle, and it proposes one of the most profound hidden symmetries ever conceived. The theory states that all the information needed to describe everything within a volume of space can be perfectly encoded on its two-dimensional boundary. Think of a hologram on your credit card. The flat, shiny surface contains all the data to project a three-dimensional image. In the same way, our universe might be a grand hologram, its full richness painted onto a distant two-dimensional screen. The roots of this mind-bending idea come from a surprising place, the study of black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, which is a measure of its hidden information, is proportional not to its volume, but to the area of its event horizon, its surface. It was as if all the data about what fell into the black hole was smeared across its spherical skin. This hinted that the true degrees of freedom in any region of space might live on its boundary, not within it. This abstract concept gained concrete mathematical form through a discovery called the anti-de Sitter conformal field theory correspondence, or AD-SCFT. It is a precise duality, a perfect symmetry between two completely different descriptions of the same physics. On one side, you have a theory of gravity, like string theory, operating in a warped, higher-dimensional space. This is the bulk. On the other side, you have a quantum field theory without any gravity at all, living on the lower-dimensional boundary of that space. The AD-SCFT correspondence is a dictionary. It states that every single event, every particle interaction, every gravitational warping that happens in the bulk has a perfect, one-to-one translation into the language of particles and forces on the boundary. A star collapsing in the interior is described as a specific thermal state on the surface. A black hole's evaporation is a scrambling of quantum information on the edge. The symmetry here is not about rotating shapes, but about the equivalence of two vastly different worlds. It is a hidden symmetry between descriptions, a clue that gravity and quantum mechanics might be two sides of the same holographic coin. If true, this means our tangible, three-dimensional experience of falling apples and orbiting planets is a magnificent illusion generated by quantum processes playing out on a distant, two-dimensional surface we can never see. The solidity of the world melts into information, and the deepest symmetry of all might be that we are living inside a cosmic code. The holographic principle shatters our perception of dimensions, but what if there is a symmetry even more fundamental than the shape of space itself? What if the laws of physics remain unchanged not just when you rotate your view, but when you zoom in or out? This is the promise of conformal symmetry, the idea that the universe might look the same at every scale. It is the principle of perfect self-similarity. Imagine a coastline viewed from space, a jagged line between land and sea. As you zoom in, you see bays and peninsulas. Zoom in further and you find rocky outcrops with their own tiny inlets. Zoom in even more and you see the intricate contours of individual grains of sand. At each level, the pattern of irregularity looks remarkably similar. The coastline is fractal, and it exhibits a kind of approximate scale invariance. Conformal symmetry proposes that the fundamental laws governing the cosmos might work in this same way. In a perfectly conformally symmetric world, there is no absolute notion of big or small, no preferred measuring stick. The physics you would discover by studying the collision of two subatomic particles would be essentially identical to the physics governing the interactions of galaxies, if you could just rescale everything appropriately. This symmetry is not just a mathematical curiosity, it is a powerful force that shaped the universe. In the first fleeting moments after the Big Bang, the cosmos was an incredibly hot, dense soup where energy was so high that particles had no mass. In that primordial fireball, the Higgs field had not yet turned on, and the distinctions between forces blurred. Many physicists believe the infant universe was in a state of perfect conformal symmetry. There was no intrinsic scale, no difference between the microscopic and the macroscopic, because everything was fundamentally massless and free. As the universe expanded and cooled, this perfect symmetry was broken. The Higgs field condensed, giving particles mass and introducing a fundamental scale. Gravity began to carve its distinct curvature into space-time. The once symmetric laws branched into the diverse forces we see today. Yet, echoes of this primordial symmetry still resonate. We see it in critical phenomena like the point where water turns to steam. At that precise critical temperature, the system becomes scale invariant. Droplets of all sizes form, from microscopic to visible, and the physics looks the same no matter how closely you look. This deep connection is formalized in conformal field theory, or CFT. These are special quantum theories that possess exact scale symmetry, and they are the tools used to describe those critical points in nature. More astonishingly, as we saw with the holographic principle, conformal field theory living on a boundary can perfectly describe gravity in the bulk. This means conformal symmetry is not just a feature of some systems, it might be the hidden key that links the quantum world to the gravitational one. It suggests that the seamless, scale-free laws governing particles are secretly describing the warping of spacetime itself. So, while our everyday world has clear scales, from the size of an atom to the span of a galaxy, these may be emergent properties like ice crystals forming in uniformly cold water. The underlying substrate of reality, the quantum code from which everything is built, might still obey that ancient perfect symmetry where size is an illusion, and the same rules apply from the infinitely small to the infinitely large. Yet even the most perfect symmetries can hide a deeper, more fundamental truth. There is a trio of operations so essential to the fabric of reality that their combined action is thought to be the universe's ultimate, unbreakable rule. This is CPT symmetry. To understand it, we must examine its three components. First, charge conjugation, or C. This is the operation of swapping every particle with its corresponding antiparticle. Turn an electron into a positron, a quark into an antiquark. It is the symmetry between matter and antimatter. Second, parity, or P. This is the operation of creating a perfect mirror image. Flip all spatial coordinates, so left becomes right, up becomes down, forward becomes backward. It tests whether the universe cares about handedness. Third, time reversal, or T. This is the operation of running the clock backwards, reversing the sequence of events, making every particle retrace its exact path. For a long time, physicists believed each of these symmetries was sacred and inviolable on its own. But the universe loves to surprise us. In the 1950s, experiments revealed that the weak nuclear force, which governs radioactive decay, blatantly violates parity symmetry. It has a profound preference for left-handedness. Certain particles always spin in a left-handed way when they decay, as if the universe itself has a favorite direction. This was a monumental shock. Then it was found that the combined operation of C and P, swapping particles and mirroring space, was also violated in some rare particle decays. Even time reversal symmetry, T, appears to be subtly broken in the oscillations of neutral kaons and B mesons. It seems the universe is not perfectly symmetrical under any one of these individual transformations. But here is where the hidden order reasserts itself with breathtaking force. While C, P, and T can each be broken, their combined product, CPT, is believed to be an absolute, unbreakable symmetry of nature. Perform all three operations together, swap matter for antimatter, reflect the universe in a mirror, and reverse the flow of time, and the resulting universe would obey exactly the same laws of physics as our own. No experiment has ever detected a violation of CPT symmetry. This is not just an empirical observation, it is a cornerstone of modern quantum field theory. The entire mathematical framework that gives us the standard model, the one that so accurately describes particles and forces, is built on the bedrock assumption that CPT symmetry must hold true. If it were ever found to be broken, the foundations of physics would crack. The implications of this perfect combined symmetry are profound, especially for the mysterious arrow of time. Our everyday experience is filled with irreversible processes. A cup shatters but never spontaneously reassembles. This directionality, this flow from past to future, is encapsulated in the second law of thermodynamics, which states that entropy or disorder always increases. CPT symmetry provides a deep link between this thermodynamic arrow and the fundamental laws. Because CPT is perfect, it means that a universe that is the CPT mirror of our own, a universe of antimatter reflected in space and running backwards in time, would evolve exactly according to our laws. In that reversed universe, an antimatter observer would see entropy increasing in what we would call the past. This suggests that the arrow of time we feel may not be written into the fundamental equations, which are CPT symmetric, but emerges from the specific, low entropy conditions of our Big Bang. The universe started in a state of exquisite order, and everything since has been the inevitable, messy unfolding from that singular point. CPT symmetry tells us that the fundamental laws are timeless and reversible, even as the stories they tell are not. It is the universe's ultimate seal of consistency, ensuring that for every possible world, there exists a perfectly valid, symmetrical twin telling its story in reverse. CPT symmetry may be perfect, but our universe is not. Look around you. Everything you see, from the stars above to the screen in front of you, is made of matter. Antimatter, its perfect symmetrical twin, is astonishingly rare. This imbalance is one of cosmology's most profound mysteries, known as the Baryon asymmetry. If the Big Bang created equal amounts of matter and antimatter, they should have annihilated each other in a flash of pure energy, leaving behind a cosmos of radiation and nothing else. The fact that we are here, that galaxies exist at all, means something tipped the scales. Our very existence is a testament to a broken symmetry. Physicists believe the universe began in a state of perfect symmetry, a seething, energetic soup where particle and antiparticle pairs were constantly created and destroyed in balance. Then, as it expanded and cooled, a subtle crack appeared in the mirror. In the 1960s, Russian physicist Andrei Sakharov outlined the three conditions necessary for this imbalance to arise from a symmetric beginning. First, there must be processes that violate the conservation of baryon number, meaning the total amount of matter can actually change. Second, there must be a violation of both charge and parity symmetry, the C and P we discussed earlier. This ensures that the processes that create matter work slightly differently than those that create antimatter. And third, these events must occur out of thermal equilibrium, meaning the universe must be changing rapidly enough that the system cannot smoothly readjust and erase the growing imbalance. Think of it like a vast, symmetrical coin-flipping contest where heads represent matter and tails represent antimatter. Initially, for every head, a tail appears. But then, the rules of the game subtly change. The coin becomes ever so slightly weighted. Now, for every 100 tails produced, 101 heads appear. Over countless flips during the universe's first fractions of a second, that tiny bias, that broken symmetry, accumulated into all the matter we see today. The antimatter mostly found its match and annihilated, leaving behind the surplus matter as the raw material for everything. But what physical process could have weighted the cosmic coin? One leading idea is called leptogenesis. In this scenario, incredibly heavy, sterile neutrinos decayed in the early universe. Due to the violation of CP symmetry, these decays produced slightly more leptons, like electrons and neutrinos, than anti-leptons. Through a complex cascade of interactions, this lepton asymmetry was then converted into the baryon asymmetry we measure, turning an imbalance in one family of particles into the matter that builds protons and neutrons. Another compelling theory is electroweak baryogenesis. It proposes that the tipping point occurred during the electroweak phase transition, when the Higgs field switched on and gave particles mass. Imagine this transition not as a smooth turn of a dial, but like water freezing into ice. If it happened as a violent, bubbling process with expanding bubbles of the new phase colliding in the hot plasma, it could have created the out-of-equilibrium conditions Sakharov required. Within the walls of these colliding bubbles, CP-violating interactions could have preferentially produced more quarks than antiquarks, seeding the universe with matter. Each of these theories points to a universe that began in perfect, sterile symmetry. A single, fragile crack in that perfection, a violation of CP symmetry at a pivotal moment, allowed for a remnant of substance to survive the great annihilation. We are not the product of a perfectly balanced cosmos. We are the children of a flaw, the beautiful, complex aftermath of a symmetry broken just enough to make something from almost nothing. Our existence is a testament to a broken symmetry, a cosmic accident that left behind a universe of matter. But zoom out far enough beyond the clumps of galaxies and the vast voids, and a different kind of symmetry emerges, one so profound it forms the very bedrock of modern cosmology. This is the cosmological principle. It is a grand, simplifying assumption that the universe on its largest scales possesses two key symmetrical properties. It is homogeneous, meaning it looks roughly the same at every location, and it is isotropic, meaning it looks the same in every direction you look. No special center, no preferred edge, no cosmic up or down. Just an immense, uniform fabric of space. Think of it like the air in a room. Up close, you can see dust motes dancing in a sunbeam, feel a draft from a window. But if you could step back and perceive the room as a whole, the air appears uniformly mixed, the same in every corner. The cosmological principle asks us to take that perspective on the entire cosmos. This idea of large-scale symmetry is not just philosophical, it is powerfully practical. It is what allows cosmologists to write down equations for the entire universe. By assuming homogeneity and isotropy, the fantastically complex general theory of relativity, which describes the warping of space-time, simplifies dramatically into the Friedmann equations. These equations are the master keys to cosmic history. They tell us how the universe expands, how its density changes over time, and they directly predict the existence of the Big Bang itself. Without the symmetrical foundation of the cosmological principle, we would have no coherent model of the cosmos. But is this principle actually true or just a convenient fiction? The most stunning evidence comes from the oldest light we can see, the cosmic microwave background radiation. This is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old, a hot, dense plasma that finally became transparent. When we map this radiation across the entire sky, the result is breathtaking. It is almost perfectly uniform. The temperature is the same in every direction to within 1 part in 100,000. That is like looking at a sheet of metal heated to white hot and finding that its temperature varies by less than 1,000th of a degree from one spot to another. This incredible smoothness is the smoking gun for the young universe's homogeneity and isotropy. The tiny fluctuations you see in those famous mottled maps, the slight blues and reds, are not imperfections. They are the seeds, those microscopic ripples in density frozen into that ancient light, are the symmetrical universe's slight asymmetries, the places where gravity began its work. From that near-perfect uniformity over billions of years, gravity amplified those tiny differences, pulling matter into the clusters, filaments, and galaxies we see today. So the cosmological principle reveals a profound duality. The universe on the largest scale is a sea of majestic symmetry, a smooth, expanding canvas. Yet it is the faintest whispers of asymmetry within that sea, imprinted at the beginning, that gave rise to all the complex structure within it, including us. It is the ultimate example of a hidden symmetry that both governs the whole and, by its gentle breaking, creates everything we know. The near-perfect symmetry of our cosmic canvas hints at a deeper, more unsettling possibility. What if the specific laws we observe, the exact strength of gravity, the mass of the electron, even the fact that we have 3 dimensions of space, are not fundamental truths at all? They might simply be local bylaws, the random outcome of a cosmic lottery drawn from an infinite array of possibilities. This is the multiverse, and within it lies a new kind of hidden symmetry, a meta-symmetry across all possible realities. One compelling path to this vast ensemble is eternal inflation. Picture the Big Bang not as a single explosive event, but as the beginning of an endlessly bubbling sea of spacetime. In this view, our entire observable universe is just one bubble that nucleated in a much larger, eternally inflating meta-universe. The inflationary field, the energy that drove the rapid expansion of our cosmos, does not switch off everywhere at once. Like a pot of water boiling forever, new bubbles of stable spacetime continuously form in the eternally inflating background. Each of these bubble universes undergoes its own version of a Big Bang, cooling and settling into its own unique vacuum state. And here is the critical point: the specific properties of that vacuum determine the local laws of physics. The energy of the vacuum sets the cosmological constant, the strength of the forces, and the masses of particles. In different bubbles, these values are different. In some, the cosmological constant might be enormous, causing the universe to rip itself apart instantly. In others, the weak nuclear force might be too feeble to forge the elements necessary for stars. Our universe, with its seemingly fine-tuned constants that allow for complexity and life, is just one bubble among an unfathomable number. This concept finds a startling parallel in string theory's landscape. Recall the countless possible Calabi-Yau shapes for the extra dimensions, perhaps as many as 10 to the 500. Each distinct shape corresponds to a different vacuum state, a different set of physical laws and particle content. The landscape is the mathematical map of all these possible universes inherent within string theory. Eternal inflation, then, becomes the process that randomly samples this landscape. As bubbles form, they crystallize one of these many possible configurations. In this grand picture, the symmetry is no longer within a single universe. It is the symmetry of the generating process itself. The meta-law, the rule of eternal inflation, or the structure of the string landscape, is symmetrical and unchanging. It treats all possible outcomes, all possible sets of broken symmetries equally. Our particular reality, with its specific Higgs mechanism and its 3 generations of matter, is not special or inevitable. It is simply one roll of the dice in a cosmic casino that has been rolling forever. This shifts the question of why our universe is the way it is from physics to statistics. We do not observe a universe with no stars or one that collapsed immediately, because in those universes there is no one to ask the question. Our existence as observers acts as a filter, selecting for the rare bubbles where the constants allow for galaxies, planets, and life. The profound, and some would say troubling, implication is that the deepest symmetries we seek to uncover may not be the unique blueprint of reality, but merely the parochial rules of our local cosmic neighborhood, a single page in an infinite library of physical law. The multiverse paints a picture of endless possibility, but when we look at our own specific universe with the most precise instruments ever built, we find something unsettling. The cosmic microwave background, that near-perfect echo of the Big Bang, holds faint whispers that defy our expectations of symmetry. These are the cosmic anomalies, and the most famous of them is known with dramatic flair as the axis of evil. This is not a malevolent force, but a statistical ghost in the machine. When scientists analyze the intricate pattern of hot and cold spots in the ancient light, they expect a random distribution, a testament to the isotropy of the early universe. But several large-scale features seem to align in a peculiar way. Certain patterns of fluctuation appear to be coordinated across vast swaths of the sky, hinting at a possible preferred direction, a subtle axis running through space. It is as if the universe's fingerprint has a faint, unexpected swirl that points somewhere. This alignment, if real, would be a direct challenge to the cosmological principle's assumption of isotropy, the idea that the universe looks the same in every direction. The name Axis of Evil is partly a joke about its unnerving implications, suggesting a crack in the foundation of modern cosmology. Alongside this, other anomalies deepen the mystery. There is the cold spot, an unusually large and frigid region in the cosmic microwave background that is far colder than our standard models can easily explain. Some have speculated it could be a sign of a cosmic texture, a defect in the structure of space-time left over from the early universe, or even evidence of a collision with another bubble universe in the multiverse. Then there is the Hubble tension, a growing discrepancy in how fast the universe is expanding. Measurements based on the cosmic microwave background predict one rate, while observations of nearby stars and galaxies yield a consistently faster one. This is not a small error, it is a significant gap that has resisted all attempts at reconciliation. These anomalies are not necessarily proof that our core theories are wrong, but they are powerful indicators that our map of cosmic symmetry is incomplete. They are the cosmic equivalent of finding a single, perfectly straight seam on what you thought was a hand-carved, irregular stone. It suggests a design or a process we have not yet accounted for. Could these cracks be mere statistical flukes, the universe rolling a few improbable dice? Absolutely. But they could also be clues pointing to a deeper layer of reality, one where our assumptions of perfect large-scale symmetry are approximations of a more complex and perhaps even more beautiful hidden order. Perhaps the universe is not simply homogeneous, but possesses a higher dimensional symmetry that only manifests as these strange alignments in our three-dimensional view. Or maybe these anomalies are the echoes of the universe's birth pangs, imprints from a time before inflation smoothed everything out, a fossil record of a more chaotic, asymmetric beginning. They remind us that every symmetry we hold sacred is a hypothesis, waiting to be tested by the next, deeper look into the cosmos. Amidst the grand frameworks of strings and multiverses, one physicist dared to propose a radically different kind of map. Garrett Lissy, a surfer and independent researcher, put forward an idea of breathtaking mathematical elegance he called an exceptionally simple theory of everything. Its core was not extra dimensions or vibrating strings, but a single, spectacularly complex geometric object, the E8 Lie group. In the world of mathematics, Lie groups describe the continuous symmetries of smooth shapes. The rotations of a sphere, for instance, form a simple Lie group. Lissy's audacious suggestion was that the entire zoo of particles and forces in our universe, gravity included, could be represented as symmetries of one specific, exceptionally beautiful shape, the E8 polytope. This structure exists in an abstract 248-dimensional space, and its symmetry is described by the E8 Lie group, considered by many mathematicians to be the most exquisite and complex of all simple Lie groups. To visualize it, picture not a shape in our world, but the shadow it casts. The intricate, 8-dimensional root system of E8 can be projected down to 2 dimensions, creating a mesmerizing, flower-like pattern of 240 interlocking points and lines, a kaleidoscopic mandala of cosmic geometry. Lissy's proposal was that every known fundamental particle, from the electron to the Higgs boson, corresponds to a specific point or symmetry within this 248-dimensional structure. The different forces, including gravity, emerge naturally from the interactions between these points as the geometry of the shape is rotated in its abstract space. In this view, the standard model is not a patchwork of separate symmetries, but merely one facet of a single, unified, and profoundly symmetrical jewel. The theory was met with a firestorm of fascination and skepticism. Its beauty was undeniable, a siren call to those who believed the universe's deepest truths must be mathematically gorgeous. It promised a unification without extra dimensions or supersymmetry, using a mathematical object already revered for its perfection. Yet the challenges were immense. Translating the abstract mathematics into testable, quantitative predictions about particle masses and interaction strengths proved extraordinarily difficult. The physics community largely viewed the proposal as incomplete, a stunning sketch that lacked the rigorous engineering to build a working universe. Furthermore, the theory struggled to incorporate key features like chiral fermions, the handedness of particles that is so crucial to the weak force. While Lissy and collaborators continued to refine the idea, it remains on the fringe, a magnificent what-if carved from pure geometry. Yet its legacy endures as a powerful reminder. It challenges the assumption that a theory of everything must be baroque and inaccessible. It dares to ask if the universe's hidden symmetry might not be found in unseen dimensions or infinite bubbles, but in the perfect, singular geometry of a mathematical object waiting to be understood. The search for hidden symmetry often leads us to build upon the world we see, adding dimensions or vibrating strings. But what if we are building on the wrong foundation entirely? Roger Penrose, the Nobel laureate who helped prove black holes are real, proposed a breathtaking inversion. He suggested that space-time itself, the very stage of reality, is not fundamental. It is a secondary, emergent phenomenon. The true, deeper reality is a realm of pure light and geometry called twistor space. In this radical vision, twistors are the primary objects, and our familiar four-dimensional universe is merely a shadow they cast. A twistor is not a particle in space-time. It is a more abstract entity that elegantly encodes both a point in space and the momentum and spin of a light ray or null ray passing through that point. Think of it this way: in our world, you describe a beam of light by saying where it is and where it is going. In Twister space, that entire description, the beam's identity, is a single point. This flip in perspective unlocks a hidden symmetry of staggering beauty, because the geometry of Twister space is deeply connected to the conformal symmetry of a celestial sphere. Calculations of particle interactions, especially the scattering of massless particles like gluons, which are fiendishly complex in traditional quantum field theory, become astonishingly simple and elegant in the language of twisters. The messy, looping Feynman diagrams simplify into graceful geometric constructions in twister space, where the underlying symmetry of the system shines through unobscured. This hints that the profound conformal symmetry we sense in nature is not an accident, but a direct reflection of this more fundamental twister geometry. Penrose's ultimate hope was that twister theory would provide a natural home for uniting quantum mechanics with Einstein's gravity. In this view, the smooth curvature of spacetime would not be a primary field, but a large-scale, statistical approximation of the quantum entanglement of countless twisters. The fabric of the cosmos would be woven from threads of light and information. While a full theory of quantum gravity from twisters remains elusive, its legacy is profound. It teaches us that the symmetries we seek might require us to abandon our most basic assumptions, to step outside the stage and examine the theater from a higher, more symmetrical vantage point, where points dissolve and light itself becomes the fundamental coordinate. Hidden within the equations that describe our universe might be a pattern of such precise beauty that it leaves no room for chance. Some unified theories propose that the fundamental numbers of nature, the exact strength of the forces, the delicate ratios between particle masses, are not arbitrary outcomes of a broken symmetry or a random bubble in the multiverse. They are fixed, immutable digits locked into place by a higher mathematical harmony. This harmony is the domain of modular forms, functions of profound and intricate symmetry that could be the universe's ultimate architectural blueprint. To grasp their significance, we must step into a world where mathematics and physics become indistinguishable. Modular forms are special functions that live on the complex plane, and they possess an almost magical property. They remain unchanged under a vast group of transformations. Imagine a mosaic so perfectly designed that you could shift it, rotate it, stretch it in specific ways, and the entire pattern would snap back into place, looking exactly the same. That is the essence of modular symmetry. These functions are not just mathematical curiosities, they are the heroes of one of the greatest intellectual triumphs in history, the proof of Fermat's last theorem. Their deep symmetry was the key to unlocking a problem that had stumped mathematicians for centuries. Now, physicists wonder if that same key might unlock the cosmos. The audacious idea is this: the specific modular form that describes our universe, its unique symmetrical fingerprint, directly determines the numerical values we measure in particle physics. The so-called coupling constants, which dictate how strongly particles interact, and the mass ratios, like why the top quark is so much heavier than the electron, would not be free parameters to be tweaked. They would be outputs, calculated numbers forced upon us by the rigid, symmetrical structure of the modular form. In this view, asking why the fine structure constant is approximately 1 over 137 is like asking why a snowflake has 6 points. It is an inevitable consequence of its underlying crystalline symmetry. This concept moves us from a universe of flexible possibilities to one of mathematical destiny. It suggests that if we could ever identify the correct modular symmetry group governing all forces, we could, in principle, derive every fundamental constant from pure logic and geometry. The chaotic menagerie of the Standard Model would be revealed as a single, elegant equation, a symphony written in the language of modular forms. The search for this master symmetry is a quest to find the one true pattern from which all of reality is cut. A pattern so perfectly balanced that it allows for no variation, a final answer written not in the stars but in the timeless realm of numbers. While some theories seek symmetry in higher dimensions or abstract mathematics, others take a radically minimalist approach. They start with almost nothing and ask how everything we know could possibly arise. One of the most striking examples is causal dynamical triangulations. Forget strings, forget extra dimensions. This theory suggests that space-time itself, the smooth, continuous fabric of our reality, is not fundamental. It is an illusion, a large-scale mirage that emerges from a chaotic, formless quantum soup. The building blocks could not be simpler. Imagine the most basic geometric shape you can, a triangle. Now give it a dimension of time, making it a tiny, four-dimensional chunk called a simplex. These are the atoms of space-time in this theory. Physicists, through massive computer simulations, take countless numbers of these microscopic geometric pieces and glue them together randomly, following only two basic rules. The connections must respect causality, meaning cause must always precede effect, and the overall construction must have a fixed topology, preventing wild, disconnected shapes from forming. They then let the simulation run, watching how this vast, jumbled network of triangles behaves as they dial the parameters. The results are nothing short of magical. Under the right conditions, this chaotic soup of geometric bits does not remain a disordered mess. It spontaneously organizes itself. The countless tiny triangles coalesce and smooth out, giving rise to a large-scale structure that behaves exactly like a four-dimensional universe, complete with the familiar three dimensions of space and one of time. The smooth, symmetrical spacetime described by Einstein's general relativity does not need to be put into the equations at the start. It emerges like a crystalline structure freezing from water. The profound symmetry of general relativity, its indifference to any particular coordinate system, is not an input in this model. It is an output, a hidden order that arises naturally from the chaotic dance of its fundamental parts. This suggests a breathtaking possibility. The majestic symmetry of our expanding cosmos, the elegant curvature that guides planets and light, might not be a law written into the universe's foundation. It could be a collective phenomenon, a pattern of stability that forms when enough quantum building blocks come together, much like the predictable flow of a liquid emerges from the frantic, random motion of its molecules. In this view, we are not living on a pre-fabricated stage, but on a tapestry that is constantly weaving itself into existence, its perfect symmetry born from elemental chaos. The emergence of spacetime from chaos points to a universe that finds order on its own. But what if this self-organization is not just a happy accident? What if the laws of physics themselves are the simplest possible rules that could ever give rise to a cosmos like ours? This is the simplicity postulate, a theory that posits a profound hidden symmetry between law and outcome. It suggests the universe is not governed by arbitrarily complex equations, but by the most elegant, minimal set of instructions that can still generate stars, planets, and conscious observers. Think of it as nature's own version of Occam's razor, the principle that the simplest explanation is usually the best. In this cosmic context, simplicity is not just a preference, it is a form of deep symmetry. A law that is unnecessarily convoluted would be asymmetrical, cluttered with arbitrary additions that serve no purpose. The universe, according to this view, prefers the clean, symmetrical lines of a minimal blueprint. We can frame this idea through algorithmic information theory, which measures the complexity of an object by the length of the shortest computer program needed to generate it. A perfectly symmetrical circle has a very short program, just a few lines of code defining a center and a radius. A random splatter of paint requires a program as long as a list of every pixel's color and position. The laws of our universe, when written in the language of mathematics, appear to be remarkably short programs. They are concise, symmetrical sets of rules that, when run for 13.8 billion years, produce the incredible complexity we see around us. This leads to a stunning inversion of perspective. We often think of life and complex structures as unlikely flukes in a vast, indifferent cosmos, but the simplicity postulate turns that on its head. Perhaps complexity and life are not improbable accidents, but inevitable consequences of a universe operating under the most efficient, symmetrical laws possible. A universe governed by overly simple laws, like one with only gravity and no other forces, would remain a featureless soup of hydrogen, never complexifying. A universe governed by overly complex, arbitrary laws might collapse in on itself instantly or fly apart into meaningless noise. Our universe seems to sit in a Goldilocks zone of legislative elegance, with laws just complex enough to allow for self-organization, but simple enough to be symmetrical and beautiful. This is the symmetry of optimal design. The forces, particles, and constants we have are not a random draw. They are the minimal, necessary toolkit for building a cosmos that can compute its own existence. From this simple, symmetrical starting point, complexity emerges naturally, like an intricate snowflake crystallizing from the basic rules of water molecules bonding in a hexagonal pattern. The universe did not need a detailed blueprint for a galaxy or a brain. It only needed a few perfect, symmetrical principles, and given enough time and space, those principles inevitably gave rise to structures that could wonder about their own origin. In this light, we are not a bug in the cosmic code, we are a feature, the universe becoming aware of its own hidden, beautiful simplicity. But even the most elegant laws can lead to a terrifying paradox. At the edge of a black hole, two pillars of physics, each built on their own beautiful symmetries, collide in spectacular contradiction. This is the black hole information paradox, and its resolution may lie in a ghostly imprint called quantum hair. On one side stands Einstein's general relativity, which describes gravity as the smooth curvature of spacetime. A black hole, in this view, is a perfectly symmetrical object. Its event horizon, the point of no return, is a mathematically flawless, featureless sphere. According to the great physicist John Wheeler, black holes have no hair, meaning they possess only three distinguishing features: mass, electric charge, and spin. Everything else, every shred of information about what fell in, is obliterated, crushed into the singularity at the center. The star that died, the book you threw in, the very atoms of your body, all are lost, leaving behind a black hole that is identical to any other with the same mass, charge, and spin. This is a universe with a profound and troubling symmetry, where vastly different histories lead to the same, blank final state. On the other side stands quantum mechanics with its own sacred symmetry, unitarity. This principle states that information is never truly destroyed. It can be scrambled, transformed, hidden, but never erased from the universe. The quantum description of a system is like a perfect, unfading ledger that tracks all possibilities. If you burn a book, the information seems lost in the smoke and ash, but in principle, if you could track every particle and its quantum state with infinite precision, you could reconstruct the book. The information still exists. The paradox is stark. If a black hole swallows a book and then, over eons, slowly evaporates via Hawking radiation, what happens to the information? Does it vanish when the black hole disappears, violating quantum unitarity? Or is it somehow encoded in the radiation? For decades, this stood as an impasse, a crack in the foundation of reality. The smooth, symmetrical horizon of relativity seemed incompatible with the informational fidelity of quantum mechanics. The solution may require us to see the horizon not as a smooth, blank wall, but as a surface of unimaginably complex quantum texture. Recent work points to the existence of quantum hair. This is not hair in the traditional sense, but subtle, symmetrical patterns imprinted on the event horizon at the quantum level. When an object falls into a black hole, its presence disturbs the gravitational field in a way that leaves a permanent, albeit incredibly faint, mark on the horizon itself. Think of it like dropping a stone into a perfectly still pond. The ripples eventually fade, but the water's surface is forever minutely altered by the stone's passage. In the black hole's case, the stone is the information, and the ripples are delicate quantum gravitational waves or other fields that settle into a stable, symmetrical pattern on the horizon. This pattern, this quantum hair, is a new kind of symmetry, a hidden record. It means two black holes with identical mass, charge, and spin are not truly identical if they formed from different matter. Their quantum hairdos are different. As the black hole evaporates, this quantum information is not lost. It is slowly and chaotically leaked back out into the universe, woven into the fabric of Hawking radiation. The perfect, featureless symmetry of the classical black hole is an illusion, a coarse-grained picture. Zoom into the quantum scale, and a richer, more complex symmetry emerges, one that preserves the universe's informational ledger. This potential resolution hints at a breathtaking unity, where the smooth geometry of space-time and the preservation of quantum information are two aspects of a single, deeper truth, a hidden symmetry that keeps the cosmos logically consistent from its largest scales down to its very last bit. The paradox of the black hole horizon shows how deeply geometry is woven into the laws of physics. But another discovery reveals that geometry might not just describe reality, it might actually compute it. This is the amplituhedron, a geometric object of such stunning beauty that it seems to calculate the universe itself. For decades, physicists have relied on a powerful but notoriously messy tool to predict what happens when particles smash together in accelerators, quantum field theory. Its calculations involve summing over an infinite number of possible paths and interactions, a labyrinth of complexity represented by intricate Feynman diagrams. The results are accurate, but the process feels convoluted, like using a 1,000-piece puzzle to answer a simple yes or no question. Then, in 2013, a team of researchers made a breakthrough that cut through the clutter. They found that the scattering amplitudes, the probabilities for particles to collide and produce specific outcomes, could be derived not from endless sums, but from the volume of a single, multi-dimensional geometric shape, the amplituhedron. The name itself is a clue, combining amplitude, the quantum probability, with hedron, meaning a geometric solid. Think of it as a cosmic jewel whose facets and interior space directly encode the outcomes of particle collisions. In this formulation, the frantic dance of virtual particles and forces is replaced by the serene, static geometry of this shape. To calculate a complex scattering process, you don't trace endless diagrams, you simply find the volume of the amplituhedron corresponding to that process. The hidden symmetry here is profound. The amplituhedron's geometry possesses a property called positivity, a kind of perfect internal consistency that naturally yields the positive probabilities we observe in nature. Its very structure enforces the unitarity and locality we expect from physics, but it does so from a higher, more symmetrical vantage point. Most astonishingly, this geometric picture does not require space-time or locality, the idea that particles interact only at points, to be fundamental ingredients. Space-time and our familiar notions of cause and effect emerge from the geometry, not the other way around. It is as if we have been studying the shadows on the wall of Plato's cave, and the amplituhedron is the true object casting those shadows. This discovery suggests that the deepest laws of the quantum world are not about forces pushing and pulling in a pre-existing arena. They are about the relationships between abstract geometric quantities, relationships of such perfect harmony that they generate the universe of our experience. The messy quantum world, with its probabilities and uncertainties, is revealed to be the elegant, inevitable consequence of a hidden geometric symmetry, a silent calculation performed by a shape of breathtaking simplicity. If geometry can compute reality, then what is the fabric of space itself made of? The answer may lie in the most mysterious connection in the quantum world. Two particles can become entangled, linked across vast distances in such a way that measuring one instantly determines the state of the other. A ghostly correlation that Einstein famously dismissed as spooky action at a distance. For nearly a century, entanglement and the smooth geometry of spacetime described by Einstein's equations were seen as entirely separate concepts, one belonging to the quantum realm, the other to gravity. But a revolutionary conjecture known as ER equals EPR proposes they are one and the same thing. This idea suggests a hidden symmetry of staggering elegance, that an Einstein-Rosen bridge, the theoretical wormhole connecting two points in space, is physically equivalent to a pair of entangled particles, an Einstein-Podolsky-Rosen pair. In this view, the spooky link is not a force acting through space, it is space. The conjecture builds a direct bridge between two of Einstein's greatest insights, his work on wormholes with Nathan Rosen and his critique of quantum entanglement with Boris Podolsky and Rosen. The ER equals EPR proposal states that if you have two black holes that are quantum entangled, the spacetime connecting them is not empty. It is threaded by a microscopic wormhole, a geometric tunnel. The greater the entanglement between the black holes, the shorter and more robust the wormhole becomes. Conversely, if you could somehow sever the entanglement, the wormhole would pinch off and disappear. This transforms entanglement from an abstract quantum correlation into a tangible stitch in the fabric of spacetime itself. The profound implication is an idea often called it from qubit. There it is spacetime, the stage of reality. The qubit is the basic unit of quantum information. The conjecture suggests that spacetime does not exist fundamentally. It emerges from a vast cosmic web of quantum entanglement. Picture the universe not as a blank canvas where things happen, but as a dynamic tapestry being woven in real time. Each thread in this tapestry is a quantum connection, an entangled link between particles. Where these threads are densely woven and strongly entangled, they create the illusion of smooth, continuous space. Where entanglement is weak or absent, space may become frayed or disconnected. This provides a breathtakingly symmetrical picture of cosmic connectivity. The gravitational force that bends starlight and holds galaxies together is not a fundamental pull, but a side effect of this underlying quantum network. The universe's structure, from the smallest scales to the vast cosmic web of galaxies, could be a manifestation of a single principal entanglement-building geometry. This hidden symmetry offers a potential path to unify quantum mechanics and gravity. In this framework, a black hole's interior is not a mysterious singularity cut off from the universe. It is seamlessly connected to the Hawking radiation it emits through a complex web of entanglement, potentially resolving the information paradox in a geometric way. The universe, then, is not a collection of separate things in a container. It is a single, symmetrical network of relationships, a cosmic quantum computer whose processing generates the very space and time we experience. Every connection we see, from the orbit of a planet to the bond between atoms, might be a whisper of this deeper, entangled reality. But if entanglement weaves the fabric of space, what dictates the pattern of the weave? Perhaps the universe follows not a set of rigid laws, but a simple statistical rule, a principle of maximum ignorance. This is the principle of maximum entropy, and it suggests that the physical laws we hold sacred might simply be our best guess given how little we truly know. In this view, symmetry is not a property of the cosmos, but of our reasoning about it. Imagine you are handed a strange, six-sided die. You are told it is loaded, but you have no idea how. What is the most fair, unbiased prediction you can make about the outcome of a roll? You would assume each face is equally likely, a 1 in 6 chance. This is not because you believe the die is perfectly fair, but because, given your total lack of information, assigning any other probability would be an arbitrary assumption. You have chosen the probability distribution with the maximum entropy, the one that is maximally uncertain, maximally random, and therefore maximally symmetric in its treatment of all possible outcomes. Now scale this idea up to the universe. We have some pieces of information, like the average energy in a box of gas, or the fact that the universe is expanding. The principle of maximum entropy states that, given those few constraints, the universe should look like the most random, most disordered, most unbiased arrangement possible. Astonishingly, when physicists apply this principle, the familiar laws of thermodynamics, statistical mechanics, and even quantum mechanics emerge naturally. They are not fundamental decrees, but the inevitable statistical consequences of a cosmos playing the odds with perfect fairness. This connects deeply to Bayesian probability, a framework for updating our beliefs as we gather evidence. In this picture, a physical law is not a discovered truth etched in cosmic stone. It is our current, most rational expectation, the most symmetric hypothesis that fits all the data we have observed so far. Gravity works the way it does not because it must, but because, given everything we have seen, it is the least surprising, most probable way for mass and space-time to interact. The symmetry here is profound. It is a symmetry of reasoning, a commitment to not adding extra assumptions without cause. When we derive Newton's laws or Schrödinger's equation from maximum entropy, we are essentially saying the universe shows no favoritism among all the possibilities consistent with our limited knowledge. This flips the entire quest for hidden symmetry on its head. We are not uncovering a pre-existing geometric pattern. We are imposing a pattern of perfect intellectual neutrality onto the cosmos and finding that the cosmos obliges by appearing orderly. The laws of physics, then, might be the universe's way of being as ordinary as it can be, a masterpiece of unremarkable statistics. The most unbiased universe is one that follows the rules of maximum entropy. Yet, we find ourselves in a cosmos that seems suspiciously hospitable, its laws fine-tuned to an almost impossible degree for the emergence of life. This brings us to a theory that turns the entire search for symmetry inward toward the observer. It is the anthropic principle, and it suggests that the hidden symmetry we perceive might be a form of cosmic selection bias. The principle is disarmingly simple. The universe we observe must be compatible with the existence of observers. We are not passive witnesses to a random reality, we are active products of it. Our very presence acts as a filter, selecting for the specific set of conditions, the specific broken symmetries that allow for stars, planets, and conscious life. This is not a design argument, but a statistical one. If the multiverse is real, a vast landscape of bubble universes, each with different physical constants and broken symmetries, then most of those universes would be sterile. Some might have gravity so strong they collapse instantly. Others might have a weak force too feeble to forge carbon in stellar furnaces. In those places, no one is around to ask why the laws are the way they are. We find ourselves in this particular universe with its specific strength for the weak nuclear force and its precise value for the cosmological constant, precisely because this is one of the rare islands in the multiverse where the conditions for observation are met. The apparent fine-tuning of our symmetrical laws is not a miracle, it is a necessity. Our existence imposes a meta-symmetry, a higher-order rule that says the only universes we can ever talk about are those capable of producing talkers. This perspective reframes every delicate balance we have discussed. Why does the Higgs field have just the right value to give particles mass without crushing atoms? Why is the strong nuclear force perfectly calibrated to bind nuclei, but not so strong that it consumes all hydrogen in the early universe? From an anthropic view, these are not questions with fundamental answers rooted in a unique mathematical necessity. They are environmental questions. We are like a fish marveling at how perfectly water is suited for swimming, never considering that it evolved in water and could not exist anywhere else. The symmetries we uncover, from the gauge symmetries of the standard model to the cosmological principle, are the local bylaws of our particular habitable zone in the landscape of all possible physics. This idea can feel unsettling, as if it demotes our quest for a fundamental theory, but it also introduces a new kind of elegance, a symmetry of reasoning. It tells us that the search for why our universe is the way it is cannot be separated from the question of why we are here to see it. The observer and the observed are linked in a cosmic tautology, a closed loop of cause and effect where the condition for observation sculpts the very reality that is observed. In this light, the hidden symmetry of the cosmos might be the most personal one of all, a reflection not of a distant mathematical truth, but of our own unlikely place within an infinite ensemble of possibilities. This deep link between symmetry and law is not a modern guess. It is a proven theorem, a cornerstone of physics discovered by a mathematician named Noether. In 1918, while much of the world was at war, Noether uncovered a connection of breathtaking simplicity and power. Her theorem states that for every continuous symmetry in the laws of nature, there exists a corresponding quantity that is conserved, a value that never changes. This is the hidden engine that translates the universe's abstract beauty into the concrete rules we can measure and rely upon. Consider the symmetry of space itself. The laws of physics are the same here as they are 1 meter to the left or 1 light year away. This is translational symmetry, the idea that the universe has no special, favored location. Noether's theorem tells us that this spatial symmetry directly leads to the conservation of momentum. An object's momentum, its mass times velocity, remains constant unless an external force acts upon it. This is why a spacecraft once set in motion in the frictionless void will coast forever. The symmetry of empty space guarantees it. Now think about rotational symmetry. The laws of physics do not care which direction you are facing. An experiment performed facing north will yield the same result as one facing east. This symmetry of orientation gives us the conservation of angular momentum. A spinning ice skater pulls her arms in and she spins faster. Her angular momentum, the product of her rotation and her spread, must remain constant. This principle governs everything from the pirouette of a dancer to the majestic, unwavering spin of a planet in its orbit. The cosmos itself is rotationally symmetric, and so the total angular momentum of the universe is a fixed, eternal number. Perhaps the most profound symmetry is that of time. The fundamental laws of physics do not have a preferred moment. They worked the same yesterday, they will work the same tomorrow. This temporal symmetry, according to Noether, leads to the conservation of energy. Energy can neither be created nor destroyed, it can only change form. The chemical energy in a log becomes heat and light in a fire. The gravitational potential energy of a raised weight becomes kinetic energy as it falls. The total sum remains unchanged, a direct consequence of time's uniformity. Noether's theorem is the Rosetta Stone that decodes the universe's hidden language. It tells us that the majestic conservation laws we learn in school, the very pillars of predictability in our cosmos, are not separate rules. They are the direct, inevitable offspring of the universe's deepest symmetrical nature. The fact that momentum is conserved is not a lucky accident. It is a mandate issued by the homogeneity of space. The conservation of energy is not a useful principle. It is a direct reflection of time's relentless, featureless flow. In this light, every interaction, every orbit, every transformation we observe is a dance choreographed by symmetry. Noether gave us the key to see that the universe's elegance is not just for admiration. It is the very mechanism that makes reality stable, predictable, and knowable. Noether's theorem reveals how our universe's stability is woven from symmetry. But to glimpse the ultimate source of that order, we must rewind time to its first unimaginable moments. There, physics proposes a reality of even greater perfection. Grand unified theories, or GUT, suggest that the three forces governing our world, electromagnetism, the weak force, and the strong force, were not always separate. In the searing heat of the universe's infancy, they were one, a single majestic force described by a vast, overarching symmetry, a mathematical group like SU5 or SO10. This was a cosmos of supreme simplicity where a single type of interaction governed all particles. Quarks and leptons, the building blocks of matter, were indistinguishable under this grand symmetry, different facets of the same fundamental entity. Then something happened. As the universe expanded and cooled, it crossed a critical threshold. This perfect unified symmetry broke. It shattered not randomly, but in a specific cascading pattern that gave birth to the diverse reality we inhabit. This process is called spontaneous symmetry breaking, and it is one of the most important ideas in all of physics. Picture a perfectly round, smooth dinner plate balanced precisely on its rim at the tip of a needle. The system is perfectly symmetrical. Every direction from the center is identical, but this symmetry is unstable. The slightest breath of air, the tiniest quantum fluctuation, will cause the plate to fall. When it does, it will land in one specific orientation, pointing north or east or southwest. The perfect rotational symmetry of the balanced state is broken, and the plate now picks a definite direction. Crucially, the laws of physics did not change. The gravitational pull was always there. What changed was the state of the system. It spontaneously chose one possibility from the infinite number it once contained. In the early universe, the Higgs field played a similar but far more dramatic role. As the cosmos cooled, the Higgs field underwent a series of phase transitions. Think of water. Above freezing, water molecules move freely in a liquid state that looks the same in every direction. It is symmetric. But when the temperature drops below zero, the water freezes. Ice crystals form, locking the molecules into a rigid, hexagonal lattice. The continuous symmetry of the liquid is broken. The system now has a preferred orientation, the axis of its crystal structure. Yet the fundamental laws governing H2O molecules remain unchanged. In the GUT epoch, the universe was like a superheated, symmetric liquid. As it expanded, it cooled through its own freezing points. At a critical temperature of around 10 to the 28 degrees Kelvin, the grand unified symmetry broke first. The strong force peeled away from the electroweak force, its distinct character emerging as the Higgs fields associated with the GUT condensed into a specific non-zero value. The universe's crystal structure began to form. Later, at a much lower temperature, the electroweak symmetry broke, separating the electromagnetic and weak forces. With each breaking, new particles acquired mass, and the forces gained their unique identities and ranges. The once unified particle families, quarks and leptons, became distinct, their differences frozen into the fabric of reality. This cosmic freezing left behind fossils, magnetic monopoles, incredibly dense knots of magnetic charge, should have been created in abundance during the first GUT phase transition, like cracks forming in ice. Their predicted scarcity is one of the puzzles that led to the theory of inflation. More subtly, the specific pattern of the breaking may have seeded the matter-antimatter asymmetry through processes we discussed earlier. Grand unified theories paint a picture of a cosmos born in perfect monolithic symmetry, a unity so profound it is almost impossible to fathom. The world we see, with its three distinct forces and varied particles, is the intricate crystalline pattern that formed as that primordial symmetry spontaneously froze, gifting us a universe complex enough to build stars, planets, and minds capable of tracing the story back to its elegant, hidden source. This cosmic freezing left behind a shape, a geometry imprinted on the very fabric of everything. We have explored the symmetries of forces and particles, but what about the symmetry of the stage itself? The universe may possess a global, topological symmetry, a hidden shape that dictates its ultimate fate and its largest scale structure. Cosmologists ask a deceptively simple question: is the universe flat like a sheet of paper, positively curved like the surface of a sphere, or negatively curved like a saddle? This geometry is not just about shape, it is about destiny. A flat or hyperbolic universe would expand forever, cooling into darkness. A spherical universe might eventually halt its expansion and collapse back in a cosmic reversal. Our most precise measurements, from the cosmic microwave background to the large-scale distribution of galaxies, consistently point toward a flat geometry. But flat does not necessarily mean infinite. A piece of paper is flat and infinite in theory, but take a sheet and roll it into a cylinder. The surface is still flat, it has zero curvature, but it is finite. You can walk forever in one direction and loop back to your starting point. This is the concept of a finite yet unbounded universe. Now, extend this idea into 3 dimensions. The most famous example is the 3 torus. Imagine our 3-dimensional space as the interior volume of a giant donut, but a very special kind. To visualize it, think of a cube where each face is magically connected to the opposite face. If you fly straight out through the right wall, you instantly re-enter from the left wall. Go out the top, come in from the bottom, exit through the front, reappear from the back. In such a universe, space has no edge, no boundary. It is finite because there is only so much volume inside the cube, but it is unbounded, as you could travel forever without hitting a wall. This shape possesses a profound topological symmetry. The universe would be perfectly periodic, repeating its pattern on the largest imaginable scale. If you had a telescope powerful enough to see through one of these connected faces, you would not see a copy of the universe. You would see our own universe from a different angle. You might even see a ghostly duplicate image of our own Milky Way galaxy, or rather, the light from our galaxy that has traveled all the way around the cosmic donut and returned. This repeating symmetry would leave subtle fingerprints. The cosmic microwave background, that ancient snapshot, would show matching patterns of hot and cold spots on opposite sides of the sky, circles where the temperature fluctuations are eerily identical because they are actually the same physical region seen from 2 different paths. Scientists have searched for these telltale circles in the data. So far, no definitive evidence has been found, but the search continues. A universe with a non-trivial topology like a 3 torus would be a cosmos of ultimate closure and symmetry, a cosmic hall of mirrors where every journey outward is also a journey home, and the largest scale structure reflects a perfect hidden order. The bizarre quantum world, with its probabilities and superpositions, seems utterly alien to our solid, predictable reality, yet we are made of quantum particles. How does the fuzzy, uncertain domain of the quantum give rise to the definite, classical world we all agree upon? The answer may lie in a process of natural selection, not for life but for information. This is quantum Darwinism, a theory that explains how objective reality emerges from the quantum soup through a hidden symmetry of redundancy. At the heart of quantum mechanics is the principle of superposition. A particle like an electron can exist in multiple states at once, spinning both clockwise and counterclockwise until it is measured. Upon measurement, this wave of possibilities collapses into a single, definite outcome. But who or what performs this measurement? The traditional Copenhagen interpretation places the observer in a special, almost mystical role. Quantum Darwinism offers a more natural, physical explanation. It states that the environment is constantly measuring everything. Every particle is surrounded by a cloud of photons, air molecules, and other particles. These environmental constituents continuously interact with the quantum system, but they do so in a specific way. They act as witnesses. Imagine a single, fragile soap bubble floating in a room. This bubble represents a quantum system in a delicate superposition. Now, send a single photon of light to bounce off it. That photon carries away a tiny piece of information about the bubble's state, but it's not enough to define it. The bubble remains wobbly, uncertain, but what happens when not one, but trillions upon trillions of photons, air currents, and dust particles constantly bombard the bubble? Each interaction imprints a copy of the same, most stable information about the bubble onto the environment. Is it there? Yes. Where is it? Right there. Its position and other robust properties get redundantly copied, broadcasted, and scattered into the world. The fragile quantum superposition cannot survive this relentless copying process. It's like a secret whispered to one person. It might remain secret, but if that secret is broadcast on every television and radio station, printed in every newspaper, it becomes an objective public fact. The environment, through countless tiny interactions, performs a Darwinian selection on quantum states. Only the states that are stable, that can be reliably copied and transmitted without being easily disrupted, survive this process. These are the pointer states, and they correspond to the classical properties we know, like position and momentum. The superpositions that are fragile and cannot be copied effectively die out, drowned in the noise. This is where the profound hidden symmetry reveals itself. The symmetry is not in the quantum system alone, but in the relationship between the system and its environment. It is a symmetry of information. The same classical fact, the position of a chair, the spin of an atom, is recorded not once, but in countless nearly identical ways across the environment. You see the chair with your eyes, which capture photons that have scattered off it. You feel it with your hand as molecules in your skin interact with its surface. A microphone in the room records the sound of it scraping the floor. Each of these records is a separate, redundant imprint of the same objective reality. This massive redundancy is the symmetry that makes reality feel solid and universal. Because the information is everywhere, any observer, whether a person, a camera, or a scientific instrument, will access the same answer by interacting with just a small fragment of the environmental record. We don't need to probe the deepest quantum core of the chair. We simply intercept a few of the trillions of photons that have already been imprinted with the message, "The chair is here." Our shared classical world emerges from this democratic consensus written into the very fabric of our surroundings. The weird quantum underpinnings are still there, but they are hidden, protected by the sheer weight of copied information. In this view, the objectivity we experience is not a fundamental feature of the universe, but a consequence of a hidden symmetry of replication, where the most copyable states are the ones that shape our shared reality. Our shared reality emerges from a sea of copied information, a consensus so stable it feels like a solid stage. But what if that stage, space-time itself, is not a smooth, featureless continuum? What if, at the very smallest scales, it possesses a crystalline structure? This leads us to a theory where the fabric of the cosmos is not soft and pliable like fabric, but rigid and geometric like a lattice. It is the idea of crystallographic defects in space-time. Imagine the most perfect diamond, an endless lattice of carbon atoms arranged in a perfectly repeating, symmetrical pattern. This flawless crystal represents a pristine, empty vacuum. Now introduce a flaw. Perhaps one atom is missing, creating a vacancy, or maybe an extra row of atoms is squeezed in, bending the lattice around it. These imperfections are called crystallographic defects, and in a space-time crystal, they could be everything. In this radical picture, what we perceive as fundamental particles might not be objects moving through space, but the defects themselves. An electron could be a dislocation, a twist in the space-time lattice. A photon might be a vibration, a phonon, traveling through the crystalline structure. Even charge and spin could be properties of how the lattice is deformed around the defect. The profound implication is a complete inversion of perspective. We are not made of things inhabiting a container. We are the twists and knots in the container's very substance. The perfect, symmetrical laws of physics we have been exploring would then simply be the natural laws of this crystalline geometry. The gauge symmetries of the standard model would reflect the underlying symmetry group of the spacetime lattice, much like the rotational symmetries of a cubic crystal dictate how it can be turned and still look the same. But where does the rich diversity of particles come from? From broken symmetry. In a perfect crystal, every location is identical, but a defect breaks that translational symmetry. It creates a unique site, a place where the perfect order is disrupted. Different types of defects, dislocations, disclinations, interstitials, each with their own geometric signature, could correspond to different particles with distinct properties like mass and charge. A dislocation might have an intrinsic tension, a rest mass. A disclination, a wedge-shaped defect, might carry a topological charge. In this universe, the search for a unified theory becomes a search for the master geometry of the spacetime crystal. The quest to explain why we have 3 generations of matter or the exact strengths of the forces transforms into understanding why only certain types of defects are stable and allowed within this cosmic latticework. This theory provides a startlingly concrete image for ideas we have already encountered. The Higgs field could be like a strain field permeating the crystal, giving different defects different effective masses as they move through it. A black hole singularity might be an unimaginably dense tangle of defects, a catastrophic fracture in the lattice itself. While purely theoretical and far from proven, the crystallographic model offers a breathtakingly tangible vision. It suggests that the deepest hidden symmetry of all is architectural, the perfect repeating pattern of reality's foundation. And we and everything we see are the beautiful imperfections, the cosmic cracks that let in the light of existence. A crystal's perfection is defined by its repeating pattern in space. But what if order could repeat not just in space, but in time itself? This is not science fiction, but a new state of matter confirmed in laboratories around the world, the time crystal. It represents a radical departure from everything we know about equilibrium. Normal crystals like diamonds or salt break the continuous symmetry of space. A liquid is the same in every direction, but a crystal picks a specific lattice spacing, a specific orientation. It spontaneously breaks spatial symmetry. A time crystal does something analogous for time. In its ground state, its state of lowest energy, it does not sit still. It undergoes periodic motion like ticking without any energy input. It spontaneously breaks time translation symmetry. In a universe governed by laws that are the same at every moment, the time crystal picks a specific rhythm, a specific phase for its oscillation. This creates a new, exotic form of symmetry, not under continuous time shifts but under discrete ones. If you observe the crystal and then wait exactly one period of its internal ticking, the system will look exactly the same as when you started. It is symmetric under that specific jump in time. This is profoundly strange because it defies our classical intuition about equilibrium. A pendulum at rest in its lowest energy state does not swing. But a time crystal's ground state is dynamic, a perpetual dance at the quantum level, sustained not by energy flow but by the system's own intricate many-body interactions and quantum entanglement. Scientists have created these exotic states in trapped chains of ions, within diamond lattices with dense nitrogen vacancies, and even using a quantum computer. They pump the system just once to initiate the state, and then it settles into its persistent, protected oscillation, ticking like a clock that winds itself. The discovery of time crystals forces us to expand our definition of order. It reveals that symmetry breaking is not confined to the spatial realm. The universe may harbor forms of organization that are inherently dynamic, patterns that repeat not across space but across the dimension of time. This leads to a mind-boggling possibility, one that whispers at the edge of cosmology. Could the universe itself be in a similar, dynamically ordered state? Is the cosmic expansion, the rhythmic pulse of galactic formation, or even the arrow of time itself, a manifestation of a deeper, time crystalline structure underlying reality? We are only beginning to learn the language of this non-equilibrium symmetry, a hidden rhythm that might be ticking at the heart of everything. The ticking of a time crystal reveals a universe that can hold rhythm without energy. But beneath even that exotic dance lies a more fundamental and more puzzling state, the quantum vacuum. We often think of empty space as pure nothingness, a silent void between the stars. That could not be further from the truth. The vacuum is a seething, boiling sea of potential. At the quantum level, empty space is never truly empty. It is a roiling ocean of virtual particles, pairs of matter and antimatter that wink into and out of existence in a fleeting dance permitted by Heisenberg's uncertainty principle. This quantum foam is not a metaphor. It is a physical reality with measurable consequences, like the Casimir effect, where two metal plates placed incredibly close together in a vacuum are gently pushed together by the pressure of virtual particles outside them. The vacuum, therefore, is not a passive stage. It is an active, energetic medium, the lowest possible energy state of a quantum field. And this state may possess a profound hidden property, scale symmetry. In a perfectly scale symmetric vacuum, the physics would look identical at every possible energy level. Zoom in to examine the fabric of space-time at the Planck scale, or zoom out to view it across galactic distances, and the fundamental description of the vacuum would remain unchanged. Its energetic properties would be self-similar, a perfect fractal of potential. This symmetry is incredibly powerful, but it leads directly to one of the most embarrassing failures in modern physics, the cosmological constant problem. The energy of this seething quantum vacuum, the sum of all those fleeting virtual particle fluctuations, should contribute to the curvature of spacetime. According to Einstein's equations, this vacuum energy density acts as a cosmological constant, a force that either accelerates or decelerates the expansion of the universe. When physicists attempt to calculate this energy using our known quantum field theories, they get a number so astronomically large it is absurd. The predicted vacuum energy should be around 120 orders of magnitude stronger than what we actually observe. A universe with that much vacuum energy would have blown itself apart in the first instant of the Big Bang, never forming a single atom, let alone a galaxy. Yet, when astronomers measure the actual expansion rate of the cosmos, they find a tiny, positive cosmological constant, a gentle nudge causing acceleration. The discrepancy is not a small error. It is the worst mismatch between theory and observation in the history of science. It means our understanding of the vacuum's symmetrical nature is catastrophically incomplete. How can the vacuum be scale-symmetric and seething with unimaginable energy on paper, yet appear so calm and nearly weightless in reality? One possibility is a miraculous cancellation. Perhaps the positive energy of the virtual particles is almost perfectly balanced by a negative energy associated with gravity itself, leaving only the faintest residual we see. But such a cancellation would need to be precise to 1 part in 10 to the 120, a fine-tuning so exquisite it seems like a cosmic conspiracy. Another idea is that the vacuum energy is not a constant at all, but a dynamical field that has slowly relaxed to its current small value over the age of the universe. Or perhaps our notion of scale symmetry in the vacuum is simply wrong, broken in a way we do not yet comprehend. The cosmological constant problem stands as a stark monument to the limits of our current symmetries. It tells us that the hidden order we have been tracing, for all its beauty, must have a deeper layer, a principle that reconciles the furious quantum activity of nothingness with the serene, expansive geometry of everything. That silent, seething vacuum may hold the deepest possible note. Long before quantum foam, the ancient philosopher Pythagoras listened to the cosmos and heard music. He believed the planets in their orbits produced perfect harmonies, a celestial symphony he called the music of the spheres. It was a beautiful metaphor, but modern physics is discovering it might be a literal truth, revealing a hidden symmetry written not in geometry but in vibration. This cosmic harmony manifests most clearly in orbital resonance. Look at Jupiter's inner moons, Io, Europa, and Ganymede. For every single orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This precise 1 to 2 to 4 rhythm is a Laplace resonance, a gravitational lockstep that creates an exquisitely stable, repeating pattern. It is a symmetry in time, a celestial clockwork where the moon's gravitational tugs perfectly reinforce each other, keeping their orbits synchronized over eons. This is not a rare quirk. We see it in the gaps of Saturn's rings, cleared by resonances with its moons. We see it in the rhythmic dance of planets around other stars. Resonance is a fundamental organizing principle of the cosmos, a natural preference for certain harmonious frequencies where forces balance and structures endure. Now take this idea and dive into the quantum realm. In string theory, the fundamental particles are not points but tiny, vibrating loops. Each particle's mass and charge are determined by the precise frequency, the note that the string is playing. The entire universe, in this view, is a symphony of these vibrating strings. The hidden symmetry we seek could be the resonant relationships between these fundamental frequencies. Perhaps the electron, the photon, and the quark are not random notes but part of a chord, their vibrational modes locked in a perfect mathematical ratio that defines the laws of physics, much like the resonant lock between Jupiter's moons defines their orbits. This concept extends beyond strings to the quantum fields that permeate all of space. Think of these fields as a vast cosmic instrument with an infinite number of possible vibrational modes, like the harmonics on a guitar string. The particles we see might be the most resonant, the most stable notes that this cosmic instrument naturally sustains. In the chaotic early universe, as fields cooled and settled, only the most harmonious, self-reinforcing vibrations would have persisted. The rest would have faded out like dissonant notes cancelling each other. What we are left with is the universe's preferred scale, its fundamental chord. This idea of cosmic resonance offers a breathtakingly elegant answer to why the constants of nature have the values they do. They are not arbitrary numbers. They could be the fixed intervals of a universal scale, the necessary relationships that allow the cosmic symphony to be stable and coherent. The force strengths and mass ratios might be akin to the perfect intervals in music, the octaves and fifths that sound naturally pleasing because of their simple mathematical ratios. Our universe, then, would not be a silent, geometric object but a dynamic, vibrating one. Its hidden symmetry is not just a still pattern but a living harmony. Every interaction, from the binding of an atom to the spin of a galaxy, could be seen as an interplay of resonant frequencies, a single, everlasting piece of music where we are both the audience and a fleeting, harmonious vibration within the song. This cosmic symphony of resonant frequencies suggests a universe that computes itself into existence. But what if we take that idea to its ultimate conclusion? What if the universe is not merely like a computation but is one? This is the hypothesis of the computational universe, where reality is not made of particles or fields, but of information. In this view, the cosmos is a vast, ongoing calculation, and the laws of physics are the algorithm it is running. The symmetries we have been tracing, from conservation of energy to gauge invariance, are not fundamental properties of a substance, but logical invariances within the code. They are the rules that stay the same even as the cosmic program executes step by step. This idea, sometimes called digital physics or the simulation hypothesis, proposes that at the smallest scale, space-time is not smooth but discrete, like the pixels on a screen or the bits in a computer. The universe ticks forward in finite, Planck-sized steps of time, processing information according to a fixed set of instructions. To see how this could work, we can look at a simple digital playground, cellular automata. The most famous is Conway's game of life. Imagine an infinite grid of squares, each cell either on or off, alive or dead. The system follows just 3 symmetrical rules. A live cell with 2 or 3 live neighbors survives. A dead cell with exactly 3 live neighbors becomes alive. Any other cell dies or remains dead. That is it. From this minimal, symmetrical starting algorithm, you set an initial pattern and let it run. What unfolds is astonishing. From simple seeds, complex, dynamic structures emerge, gliders that sail across the grid, stable oscillators that pulse rhythmically, even constructors that can build copies of themselves. The grid exhibits patterns, behaviors, and a form of life that feels organic, yet it is all the deterministic output of a few lines of code. The symmetry of the rules, the fact that they are the same for every cell at every step, gives rise to the complex, often symmetrical patterns you see on the screen. Now scale this idea up to reality. Perhaps our universe is a vastly more sophisticated cellular automaton, operating on a 3-dimensional grid at the Planck scale. The fundamental particles, forces, and even the curvature of spacetime could be emergent phenomena, stable patterns that arise from the local interactions of these cosmic bits. An electron might be a specific, self-perpetuating glider pattern moving through the lattice. A law like the conservation of momentum would simply be a logical invariance of the update rules, a guarantee that information about motion is preserved as the grid updates. In such a universe, the search for a theory of everything becomes the search for the ultimate algorithm, the concise program that generates our specific cosmic simulation. The symmetries we cherish would be the elegant, compressed expressions within that code. Why is the universe isotropic? Because the update rule treats all directions the same. Why do we have gauge symmetries? Because the algorithm performs certain rotations in its abstract information space without changing the output state. This perspective reframes some of our deepest puzzles. The arrow of time could be the irreversible processing of information, moving from an ordered initial state to a more disordered one. Quantum superposition might be the universe processing multiple computational paths in parallel. Even consciousness could be seen as a particularly dense and self-referential pattern of information processing within the simulation. The computational universe hypothesis does not necessarily mean we are in a simulation created by some advanced being, though that is a popular spin. It means that computation might be the fundamental stuff of reality, more basic than space, time, or matter. The cosmos is not a machine that computes, it is the computation itself. Every star, every thought, every law of physics is a pattern in the data, a manifestation of a hidden, algorithmic symmetry running in the silent processor of existence. The computational universe whispers that reality might be a perfect, logical algorithm. But what if that algorithm is not just a set of rules, but a single, breathtakingly symmetrical object? This brings us to the final frontier of thought, the dream that has driven physics for centuries, the search for a theory of everything. It is the quest for the symmetry of all symmetries. Imagine not a list of 30 separate ideas, but a single, ultimate mathematical principle, a master symmetry so profound and all-encompassing that it uniquely dictates every force, every particle, and the very stage of spacetime upon which they play. This would be the universe's foundational equation, not written in variables we tweak, but carved from pure, inevitable geometry. In this vision, the gauge symmetries of the standard model, the conformal symmetry of the quantum vacuum, the diffeomorphism symmetry of general relativity, and perhaps even the computational symmetry of reality itself would not be separate discoveries. They would all be different facets, different shadows cast by this one sublime, higher dimensional shape. It would be the source from which all other symmetries flow, and whose breaking in one specific, majestic pattern gave birth to our particular cosmos. Finding it would be the ultimate triumph of human reason. For centuries, we have been piecing together the fragments of a shattered vase, marveling at the beauty of each individual shard. A theory of everything would be the moment we finally comprehend the original, unbroken vessel, seeing how every fragment fits into a whole of unimaginable elegance. It would answer the deepest why these forces with these strengths, why this number of dimensions, why something rather than nothing. The answer would not be a shrug toward a multiverse or an anthropic accident. It would be a demonstration of mathematical necessity. The universe would be revealed not as a chaotic, contingent accident, but as the only possible logical structure that could exist with perfect, self-consistent symmetry. It would mean that beauty is not just in the eye of the beholder, it is the law of creation. The cosmos would be a necessary truth, as unavoidable as the fact that 2 + 2 = 4. This final symmetry would be the silent music underlying the quantum foam, the crystalline geometry of the vacuum, the harmonic resonance of strings. It would be the reason time has a direction and space has 3 dimensions. It would explain the value of the cosmological constant not as a finely tuned parameter, but as the only number that could emerge from the equation without breaking its perfect form. To discover it would be to read the mind of whatever we mean by existence. Yet this dream hangs before us, tantalizing and just out of reach. Our current best attempts, like string theory or loop quantum gravity, offer glimpses of this ultimate symmetry, but they remain incomplete, lost in a landscape of possibilities. The final theory may require a conceptual revolution as profound as those of relativity or quantum mechanics, a new way of seeing that makes the hidden symmetry obvious in retrospect. Perhaps it will be an equation so simple it could fit on a t-shirt, yet so deep it contains all of reality. Or perhaps it will be a shape of such complexity that only a universe-sized mind could hold it all at once. The search continues, driven by the faith that the universe is not just symmetrical in parts, but symmetrical to its core, a single, beautiful thought thinking itself into being. From the perfect logic of a master equation to the hum of a quantum computer, our journey through 30 glimpses of hidden symmetry reaches its end. We began with the rock-solid certainty of Noether's theorem, where every conservation law is a direct echo of the universe's uniform fabric. We ventured into the elegant architecture of the Standard Model, built on unbreakable gauge symmetries, and soared into the speculative realms of supersymmetry and strings, where particles have shadow partners and extra dimensions curl into shapes of exquisite beauty. We explored the holographic principle, where our 3-dimensional reality might be a projection, and wrestled with the cosmic anomalies that challenge our smoothest assumptions. We saw symmetry break to give us matter, emerge from chaos to craft spacetime, and even tick rhythmically in the form of time crystals. From the computational universe to the dream of a final, all-encompassing theory, one theme has shone through every idea: the relentless human drive to find order. This quest is not a dry academic exercise, it is the very engine of science, the profound need to look at the star-scattered darkness and believe it makes sense. Each theory, whether proven or purely poetic, is a testament to our conviction that beneath the apparent chaos, there is a pattern, a code, a symmetry waiting to be read. So the next time you look up at the night sky, see more than just points of light. See a canvas of hidden connections, a dynamic tapestry woven from principles of breathtaking elegance. Which of these 30 windows into cosmic symmetry resonated most deeply with you? Was it the tangible power of Noether's link between symmetry and law, the mind-bending possibility of a holographic universe, or the hopeful elegance of a single theory of everything? Share your thoughts in the comments below. Let us know what hidden pattern in the cosmos feels most beautifully inevitable to you. If this journey through the universe's secret order captivated you, please like this video and subscribe for more explorations into the deepest mysteries of reality. Thank you for watching, and keep looking up, not just with wonder, but with the quiet knowledge that the universe is speaking in a language of symmetry, and we are learning word by beautiful word how